Hello, everyone, and welcome to another edition of Let's Talk ETC. I have quite an illustrious guest today. I have Guido Bertoni from the Keccak team that won the NIST contest to develop SHA3, the secure hashing algorithm version 3. And to help me today with our discussion, I also have Alex Tsankov, who's a ETC enthusiast, community member, and also the CEO of P3C. So welcome, both of you guys.
Thank you.
Thanks for having me on.
All right. So let's just get right to it. Oh, by the way, first of all, thank you, Guido, for correcting me that it's pronounced Keccak. I've been pronouncing it Keccak for months and months. And so now we cleared up that the pronunciation. So why don't you kind of share a little bit about yourself, how you got involved with the Keccak team and what prepared you for that?
Yes. Just a very short introduction. So I graduated in 1999 at Politecnico di Milano, and then I started PhD in 2000. So PhD was on implementation of cryptographic algorithms. I take the degree as an electronic engineer, and basically my background was in designing hardware. After the PhD that I ended in 2004, I started working in ST Microelectronics. And in ST, I had the chance to meet Johan Demon, Gilles Van Ask, and Michael Peters, with which in 2006 we start collaborating. So I'm based in Milano. They are based near Brussels. And we start working together in designing hash algorithm. I was more in the background of implementation of cryptographic algorithm, while there was more in the implementation and design of cryptographic algorithm. And 2006 was the date where we started working, because in 2005 there was a major breakthrough in a cryptographic conference with basically the demonstration of the insecurity of SHA3. And once we started working, there was also a lot of, movement in the cryptographic community after the 2005 break of SHA3. And NIST, so National Institute of Standards and Technology, the US institute that has standardized a lot of cryptographic algorithms, decide to run a competition in starting 2007, 2008 for selecting a new hash algorithm. So basically, SHA1 and SHA2 was designed by NSA. And the selection of the parameters and the criteria in designing SHA1 and SHA2 are basically not known. So NSA designed it behind the scene and then basically presented the algorithm, and that's it. So we have the description of the algorithm, but no motivation why they have been designed like this. And SHA2 is very similar to SHA1. So once there was the demonstration that SHA1 was not secure, everybody was not feeling very confident on SHA2. And this is why there was a push to have NIST running a new competition for selecting the algorithm. So we designed Keccak, that is, so at that time now is about 11 years old. But so at that time was a very innovative type of algorithm. So compared to SHA1 and SHA2, we introduced a different new concept from the algorithm point of view. And so for instance, one of the main security target of an hash algorithm is to be resistant to collisions. So what is collisions? Is the possibility that there are two messages that once they are hashed, they give the same result. So if you find two such messages, then basically you find a collision for the hash. And this should be very complex. And the rationale behind the SHA1 and SHA2 construction was not very convincing for us. So we designed a new construction that is called sponge construction. So this is a kind of theoretical model for designing hash algorithm. And this was actually a new model that we presented. And during the competition that started in 2008 and ended in 2012, there was basically, I think, 3 conferences where there was the possibility to present a study on the hash algorithm, so to demonstrate that an algorithm is secure, but there was even the opportunity for everybody to show that maybe an algorithm was not performing very well. So there was some security issue or real attacks on the algorithm. So basically there was a 5-year period where most of the cryptographic community was focusing either in implementing algorithms, showing that it was very fast and performing very well, or to show that there was insecurity in some algorithm. Mm-hmm. And during the contest, basically starting from about 51 algorithms, there was a first cut to 14, then a second cut to 5, and then finally the announcement of the winner.
Okay, wow. So, okay, for the people that are listening, I think you said something that'll be music to their ears. So SHA-1 and SHA-2 were designed by the National Security Agency, and it wasn't a transparent public development process, but you're saying, so SHA-3 was the first of the SHA family that was developed, the public developed it, not NSA. So that's right, is that correct? Okay.
Yes. So we put a lot of effort during the design to document all of our choices in the design. So you can go to keccak.team, so that is our website, and you can find all the papers that we have produced. So when we submit the Keccak algorithm to the competition, we had a document of about 100 pages, and at the end of the competition, the document was 150 pages, where we give all our decisions. So why this constantly like this? Why there is a rotation of so amount? Why we have selected this? All with the motivation that, okay, if we do this, we think that we are safer or this is faster and so on and so forth.
So I'm curious, there's a fantastic website actually out there called shatter.io. And what it allows you to do is it allows you to create a hash collision with SHA-1.
Yep.
And I'm a little bit curious if you can kind of walk us through exactly what's going on when you're trying to create a hash collision, and as to whether or not how SHA-2 improves on SHA-1 and solves that problem. Because SHA-2 is used very heavily throughout the cryptocurrency space and Bitcoin and all of those systems.
Yeah. So in the case of SHA-1, so basically there is now, let's say, this website, but this website is the result of many years of study in the design of SHA-1. So basically a kind of reverse engineering of the algorithm. So you have the description of the algorithm, but you don't have the motivation why the algorithm has been designed in this way. So there is different researchers that has tried to find weaknesses, and in SHA-1 they found the weaknesses. So if you look at the difference between SHA-1 and SHA-2, there are different, let's say, improvement of SHA-2 over SHA-1. So first of all, the state, so the amount of bits that are kept inside the algorithm has been increased from 160 to 256. And this gives already, let's say, more security to the algorithm. The other difference is the way that the message is manipulated inside the algorithm. So there is clearly an improvement in that dimension. So that the designer has understood that there was something in SHA-1 that was not as good as it should be, and in SHA-2 there is some improvement in this way. The tricky thing is that somehow NSA did that in advance compared to the crypto community, in the sense that the research community that published the paper in in an open way. So basically, we see SHA2 published, I think, at the beginning of year 2000 or a little bit before, while the attacks on SHA1 in the public has been done in years 2005, and then there was an improvement. So somehow NSA had some hidden work done in advance on that part.
Right. So they the NIST contest. Another question about that. So were you at all kind of scared to go to compete against so many smart people? And did you think, we never have a chance of winning, or what was it like? Were you intimidated at any point in the contest?
Okay, we think that so one of the team member, that is Johan Demon, is a very well-known cryptographer, and he is also the designer of AES. So AES is the block cipher that everybody uses when you do TLS connection. So he has, really strong background and is one of the most important cryptography in the world. And he brings a lot of know-how and expertise in the Keccak. And at the beginning of the competition, we see that we presented something really new compared to what the other presented. And at the beginning, we were a little bit scared that, so maybe what we present is too new, and the concept that we are proposing will take some time before people understand why we have designed something so different and so new compared to the state of the art. And indeed, at the beginning, we had some feedback of some friends and colleagues in the crypto community that was saying, but why you design something like this that is not clear why this should be better than the other. And so at the beginning was like, just maybe we did something too radical. Then we see that while the competition was going on, we start to see that people was realize and understanding and gaining confidence that what we proposed was really new, but was also very justified. I mean, so the decision of doing something new was not just, I want to do something new and I don't care what was done in the past. No, we were bringing the know-how in design block cipher in the field of hash function. And then there was some, tools and techniques that was applied in a new field, but then people realize. And then when we arrive at the end, we really had the hope to that we can make it, and then we did it, and we're very happy about that.
Okay, so you made an educated guess. You took a risk. You had your own opinions how to improve the hashing, the state of the art of hashing, and then with the contest, you had massive peer review, and they ended up agreeing with you that your ideas, your opinions were the best ones. And so, that's a pretty great story. Alex, did you want to say something?
Yeah, so it's fascinating because I've been going through a number of papers that were written around maybe 2010, 2011, and this was just when Keccak hadn't been selected. It was the finalists. So there were a variety of other algorithms that were also vying for the SHA3 sort of designation. And one thing that I really wanted to ask you, Guido, was how do you actually run a contest for a hashing algorithm? And what are the criteria that you can use to say one of these is better or not as good as another one?
Okay, this is...
That's a good question.
Yeah, very good question. Okay, so first I can tell you, so in the case of SHA3, there was, let's say, quite simple rules. I mean, NIST in 2007 published a document saying, we are going to run a competition looking for hash algorithm that they should demonstrate to have a security level of let's say 128 to 56 bits in given security problems. And submitter should give reference code and optimized code for PC, for Intel platform, basically. And then they was giving like 6 months, if I remember well, to give feedback on this document. And they collect some feedback, and then they say, okay, now we run the competition. And at the end of the competition, so during the competition, they had a mailing list where everybody can submit, and there was, let's say, basically the official channel to send comments and to open discussion. And then there was this free workshop, free conferences where, let's say, everybody can submit papers, and NIST was deciding who would be presenting papers, so selecting who can present. And then at the end, NIST was saying, I decide the winner or the winners, or even the possibility of taking two algorithms and combine them. So taking one part of an algorithm, and then they decide just to take one algorithm. And that's it. So in general, you should, if you want to run, let's say, another competition on hash algorithm, if you really want to, I think the first thing is to define the security level. So what are the security problems that the hash algorithm should resist to? That usually is collision resistant, pre-image resistance. And in some cases, it's also very useful if you have a very specific use case that you want to satisfy, to tell, okay, I want, so for instance, there was another competition for hashing of password. So like generally, when your PC store password, it doesn't store the password, but store the hash of the password. And then a common requirement is that this hash should not be very fast. So in such a way that brute forcing is not easy. And so you may have some very specific application requirements in terms of performances. So like you want the hash algorithm to work very well on mobile phone or IoT device or on satellite or on very big data center. And then let's say define, okay, what is the target that you want to have. So the faster and the more secure will win, and something like this.
Oh, wow. You just gave so many, I didn't realize you just gave so many good examples. Some people want a fast hash algorithm. Some people want a slow one. Some people want one that has a small memory footprint. So you can't just necessarily make one algorithm to please everybody. So yes.
But this is also, in some cases, this is also the case of Keccak. So Keccak performs really, really well in hardware and perform well on many software platforms. While there was other algorithm that was performing better in software, maybe in high-end platform, but was performing really bad in hardware. So there was this, let's say, different scenario that was also reflecting in some cases the background of the team. So like we were coming from a company that was doing chips, so we know very well how the hardware is done, while there was other that was coming more from the computer science background that was more, let's say, used to develop software and not really on the hardware side.
Interesting.
That's fascinating because, as you're familiar in the cryptocurrency and the blockchain space, people are running these hashing algorithms on what are called mining rigs. And you have these tremendous amounts of hash power being generated. I think that the Bitcoin network does people have said it's the biggest computer on earth if you just view hash power as an operation. Yeah. And I was really curious. I was reading and I saw that Keccak is 4 times faster on hardware than SHA3 is. And I was kind of curious, why do you think that is? And where do you think that speed increase comes from?
Yeah. Okay, we know very well, and it's not by chance. So one of the building blocks of SHA1 and SHA2 is modular addition. So where you take two words of 32-bit and you add them modulus 2 to the 32. So basically, you just get rid of the carry if you have an overflow and so on. So we decide to not design Keccak based on modular addition, but all the operations are basically bitwise operations. So we just perform AND between 2 bits, XOR between 2 bits, and these are the basic operations that we use. So this results that when you implement in hardware, you can be much faster than SHA2. So it's really hard to compare in hardware Keccak and SHA2 because SHA2 has basically few degree of freedom when you implement in hardware, while Keccak can be implemented in many different ways. And let's see, in reality, you can be more than 4 times faster than SHA2 if you have, let's say, basically all the freedom of the hardware implementation.
Okay, so you guys were just smarter about what was fast, what operations were fast in hardware, and so you avoided the ones that weren't so fast. That's one. Yeah. Okay. All right. Now there's another topic I wanted to ask you about. So I think it's an interesting story. You probably know that Ethereum and Ethereum Classic don't exactly use what became the official SHA3 standard, but what they use is a derivative which is now referred to as Keccak 256. And I wrote an article about that and how there was some changes that NIST proposed at the end of the contest, and there was a lot of pushback against that, and there was suspicion of a conspiracy, and the Snowden revelations had just come out. Can you kind of walk us through or share your insights?
Yes. So first of all, let's see, during the design of Keccak, we define parameters and give freedom to the user to select the parameters to tune the use of the algorithm to their needs. So the selection of the parameters in SHA3 was actually falling in the set of parameters that we suggested during the competition. So there was some, let's say, noise about the algorithm being changed, but this was not really true. So the selection of the parameters was actually in the domain that we define during the competition. To give you, let's say, an overview, because once NIST selected Keccak as the winner, we have been in contact with NIST, and NIST asked us to give some support in reviewing the standardization process that they were doing. So basically, they was writing draft and asking us to review their draft, and we were giving, let's say, our review for free, just helping them, hoping to have a good standard. So in 2013, as a Keccak team, we have been invited to Eurocrypt, that is one of the biggest conference in cryptography in Europe. John Kelsey, that is, let's say, was driving the standardization at NIST, so went to another big conference in San Francisco that was called RSA Conference to explain how and the intention to standardize Keccak in SHA3. And this was still at the beginning of 2013. During the summer of 2013, I invited John Kelsey to speak about the standardization to another workshop that is called CHESS, so Cryptographic Hardware and Embedded System, that was done in Santa Barbara and was co-located with Crypto, that is the major conference about cryptography. So basically, we have been able to go and saying, okay, NIST is going to standardize Keccak with these parameters in the 4 major conferences in cryptography during 2013. Just to say, look, if you are interested in the standard, we are going to make in this way, so that everybody could know, everybody can see, and there was an open call from NIST to say, if you think that the parameters that we are going to standardize are not fitting something, are not sounding well, just speak up, because we want to listen to you. And this, I think, was a really good move by NIST to showing that the standardization was done in a completely open way. Mm-hmm. So nevertheless, somebody was complaining, and somebody was saying that there was a change in the algorithm, and then maybe NSA was behind this algorithm. So we wrote a paper that is a page that is still on the Keccak.team website, where we're stating, no, this is still Keccak. The parameters was the one that we suggested during the competition, and we think that these are the best parameters that you should use for Keccak, and there was no weaknesses using this parameter. And so this, just to say, so there was a lot of effort, and I think that was done in the view of showing people and showing, first of all, in the major cryptographic events, what was going on, just to say, if you think this is wrong, just pick up, and understanding if it is wrong, we can do something better.
Right. So I think you've answered it, but so just to make sure, because it's an important question. So the version that Ethereum and Ethereum Classic uses, Keccak 256, as well as the official SHA3, they're all using parameters that you approved, and so you're completely confident that Keccak 256 and SHA3, and they're all secure as far as you know.
Yes, absolutely, yes.
Okay, and so it was just a misunderstanding that there was a conspiracy and that there's some funny business going on.
Fake news, somebody would say.
Yes.
We have a term for that in the crypto space. It's called FUD, fear, uncertainty, and doubt.
Well, this is coming from IBM.
Okay, yeah, okay. So now, how you talked about how there was a weakness discovered in SHA-1, and then there was concern because SHA-2 was so similar to SHA-1. Now, and it's been a number of years since Keccak was approved. Do you think it will? What is your prediction for how secure how long it's going to last before we're going to need maybe a SHA-4 contest?
Oh, I think it will take a lot of years. So at the moment, let's say so there have been a lot of let's say cryptographic technique is called cryptanalysis of Keccak by a very good cryptographer, and up to now they have shown that let's say our proposal of parameters are really safe and was very, very conservative. And recently, we designed a new version of Keccak, where basically we reduce by half the number of rounds, and we design this hash function that is called Kangaroo 12 to be very efficient when you need to do tree-hashing, so when you do to have parallel hashing. And thanks to all the work done also by other cryptographers, we have decided to reduce the number of rounds, so basically divide by half the computation, since there is very confident results that the algorithm is secure. So one point that is around since some years is the possibility to have quantum computers.
Right.
And let's say I'm not really an expert, so I read papers from time to time, and I try to understand how real could be to have, let's say, quantum computers that will be able to really break algorithms. And I have to say that most of the parameters that you can use in SHA3 has been designed in such a way that the hash function will be resistant to quantum computer as well. And this has been also study of other cryptographers. So I tend to think that unless there are, let's say, other major breakthrough that we cannot imagine, that in the next 10 years, we don't really need a SHA4.
Interesting. I'm glad you said that. I think there's probably some people listening that they maybe were thinking, what about quantum computer attacks? So if people have studied it, that are knowledgeable experts at quantum computing, and you're saying that it will likely be secure, I'm sure that's very comforting for people to hear that.
Yeah. So in the space of blockchain, so you have two major building blocks. So one is the hash that you use to do mining, and there I think, depending on the hash function that is used, you may have no problem even if there are quantum computers. While the other part is the digital signature that is based on hash, but also on a public key algorithm. And there, let's say, elliptic curves seems the most fragile algorithm. So the one that really, if you have quantum computer, you can be you can break them. So
right.
This is
yeah. So if they're in the future, hypothetically, if we hear in the New York Times about a quantum computer that was developed, then Ethereum and Ethereum Classic would have to have a hard fork to change the digital signature algorithm, but the hashing algorithm would likely be okay. They still could use Keccak. Yeah. Okay. So now this is a topic that is, I know Alex has spoken about, and I think it's an interesting question. So there's the hashing algorithm for digital signatures, which Ethereum and Ethereum Classic use, and then the mining process uses a different hashing algorithm called ETH hash, and so that was that the ETH hash development process didn't go through the same peer review like NIST had for Keccak. And so that some people wonder, is there any weaknesses, vulnerabilities that people could potentially exploit? And so Alex has discussed the idea of maybe it would be safer for Ethereum Classic to use Keccak for the mining algorithm, a peer-reviewed algorithm similar to how Bitcoin uses SHA. So does that, do you have any thoughts on that?
Yes. So indeed, let's see, the review of an algorithm is a very critical task. So we have seen that SHA1 has been used for many years and took a lot of time before someone without the knowledge of the motivation and the rationale for the construction find weaknesses in it. So the same is if someone design an algorithm without explain why the algorithm has been designed this way, for the other cryptographers that want to analyze, it's very hard to state yes, this algorithm is secure. So design its own algorithm is something that is very risky if you don't know what you are doing. And so this competition like SHA3 or like AES has been told to be very good because has focused the research effort of a large community on few algorithms. And then there was an incentive for many researchers to say, okay, if I break this algorithm, then I can publish a paper and I can demonstrate that I'm a good cryptographer. While the bad thing that I say in many blockchains is that there are, let's say, construction with algorithms that are chained in very naive way, and say maybe everything is fine, but if there are some weaknesses there, it took a lot of time before somebody can discover. And if somebody discover and they don't have, let's say, the good incentive just to say, I have found the weaknesses, but they can exploit the weaknesses, then you have very critical problems.
Right. So in case anybody's worried, there's no known weaknesses in ETH hash. So let's get that clear. Yeah. But hypothetically, if people are wondering what it would mean for somebody to find a vulnerability, so hypothetically, somebody could potentially find a vulnerability and be able to find winning blocks quickly, or find the nonce quickly, and then be able to do a 51% attack much more easily. So that would be the worst case scenario.
Yes.
But again, that's not something that we know is possible. So hypothetically, it's okay. Alex, did you want to add anything to that?
Yes. So first of all, thanks so much for chatting about that, Christian, because that's really, to me, what the biggest thing about. So the proposal is ECIP 1049. And the biggest motivation behind it is just purely from a safety perspective. I think that we really should be moving towards the safest, most well-tested algorithm. And, one of the things that's kind of interesting to me is that you have a lot of these algorithms that are hashing algorithms that are called ASIC resistant, and they're stateful. So they take some of the state of the blockchain and they use that to construct the hash. And I was curious because right off the bat, as someone who's done functional programming before, that to me seems like a big red flag. And I was curious if, Guido, do you know of any sort of stateful hashing algorithms? Is that something that ever makes sense, or what are your thoughts on that?
Yeah. Okay. So So I think what you are saying is, in the view of making, the hash, the mining ASIC resistant. Some of the proposal is to use very large state, because if you look at Keccak, there is a state, but it's just 1600 bits. While if you take the case of hash, in the case of Ethereum, then now I think you have some gigabyte of state. So
the 3 gigs, I think,
is radically different. And the idea is, if you want to build a custom hardware for doing this, the cost of memory or the cost of having very fast memory is too high, and then no one will produce a custom hardware for doing it. And then people will do mining using GPU, and then it's basically a more, democratic way of building the mining pools. So this is one point. The other, I think, yes, there has been a study on making a kind of stateful hash. I don't have at the moment in my mind, a good suggestion of reading or proposal. I'm pretty sure that somebody has looked at this.
So what strikes me is interesting. At the beginning of our conversation, you mentioned how different people have different requirements. Like for passwords, you actually want a slow hash algorithm. And I think it's interesting that ETH hash is yet another example of strange requirements, because they literally want it to have a large memory footprint. So everybody's got different requirements, which I think is kind of interesting. So, yeah. All right. So, what do you think is going to happen, Guido? I know you're in the thick of all this cutting edge cryptography, cryptanalysis research. What do you think? What can we expect in the next few years? I don't know if you've heard about zero knowledge proofs. I think that's exciting. There's all kinds of exciting, powerful cryptographic research happening. What are you excited about? What do you think is going to happen in the future?
So there are two competitions, actually 3 competitions running by NIST. So one is indeed on post-quantum algorithm. So mainly for signature and key agreements, so public key algorithm that could resist in the event that we have quantum computers. And this has started, I think, more than 1 year ago. And there are some really new algorithms there, very interesting. There is one that is running right now on lightweight cipher. So cryptographic algorithm for very lightweight devices. So for instance, Internet of Things, small sensors and things like that. The other thing that I think is also quite relevant for cryptocurrency community is threshold and implementation, where the basic concept is like multi-signature. So when you have a key, but you want to split this key in multiple shares in such a way that you want like 2 out of 3, so 2 parties signing over 3 or things like that. And so today we don't really have standards for this. And especially for backend or in the case of cryptocurrencies, like for exchanges or management of wallet by multiple parties, having, let's say, some standard procedures or standard algorithms will be very useful. Because today, for instance, you can do very basic, let's say, multiple signatures, just, let's say, cascade of signature, and that's pretty easy. On the quantum, I'm really fascinated by the physics of quantum computers. And I see that there is a lot of challenges, but there is also a lot of noise and speculation on, let's say, announcement of having progress. And in reality, some of these progress are small. And I don't know when we would see real quantum computers working.
Right. No, I have to applaud NIST for always being preemptive and thinking ahead. So yes, it's logical that they would want to develop quantum resistant algorithms, and so they're doing it now instead of waiting until there's a crisis. So that I like that. And then yes, I agree. We need a standard for multi-sig. And so it's good that those are being developed. I'm sure that that'll be welcomed by the community and very useful. Yes, great stuff. All right. So did I forget anything, Guido or Alex? Anything else you want to add?
I just wanted to say there was nothing more on my end. I just wanted to thank Guido and the team just for all the work that they've been doing in this space and for kind of sharing it with us.
Yeah, Guido, thanks. This has just been awesome, having somebody of your caliber and to share with us. And just, thanks for all you do. And hopefully we could chat more in the future.
Thanks to you. It was a pleasure to be with you and hope to talk to you soon.
All right. So bye for now and best wishes to both of you.
Thank you. Bye.
Right. Thanks so much, guys.
Bye.
Bye-bye.